On behalf of the Mobile Integration Solutions Laboratory within the Electronic Systems program at Texas A&M University, we would like to welcome you to the Nesi NanoRacks Embedded System Integration Board Hardware Functional Design Overview.
Here's a Nesi board. It is fully populated with all the physical components. It has a camera, CO2 sensor, SD card, and LEDs, along with other components. The following slides will show you how the hardware subsystems function.
Okay, so here we have an overview of the subsystems included on the Nesi board. All of these systems interface to and are controlled by the microcontroller, which is the PIC24. Here we have the USB, which is the power source for the Nesi board and provides access to the storage devices. The push button allows us to provide an external trigger to the microcontroller. The Nesi board has voltage divider circuitry to interface with resistive sensors. The real-time clock provides the ability to create a clock for accurate timing. Power driver subsystem is provided to power higher current devices, such as motors. The gas sensor is used to sense the amount of CO2 in an environment. The camera can be used to take JPEG photos at a resolution of 640 by 480 and communicates over UART. The SD cards are used to store data gathered by the microcontroller and use a shared SPI bus. The expansion allows for additional functionality to be added to the Nesi board. The lighting allows us to control 2 arrays of LEDs. And lastly, a PIC kit is used to program the PIC24.
This slide focuses on the PIC24 microcontroller. This is a 64-pin device that provides intelligence to the Nesi board. The diagram shows the various functions for each pin, and for the remaining slides we'll use the following designations as denoted in the legend. AN will be analog input, DI will be digital input, DO will be digital output, RP will be a remappable pin, which allows you to connect external pins to peripherals inside the microcontroller, such as pulse width modulation, UART, or SPI. SOSC will be the secondary oscillator, and U will be the unity gain buffer.
The Nesi board gets its power from the USB bus. This provides the 5-volt power and the ground reference for the system. Also on board the Nesi board is a hardware switch. This allows you to turn the board on and off. Many of the subsystems on the Nesi board must be powered with the lower voltage. This is done by using a voltage regulator to step the voltage from 5 volts down to 3.3 volts. Also, the CO2 sensor requires a higher voltage. So we use a DC to DC booster to convert the voltage up to 6 volts to power this peripheral. The PIC24 uses 3.3 volts for the digital high reference and also the analog high reference. So for the digital, it uses 3.3 volt logic, and for the analog inputs, it can read from 0 up to 3.3 volts. Also, the voltage for the USB will be provided externally via the 3.3 volt regulator. For the ground reference, we're using the same reference for the analog and digital ports. On the PIC24, it has an internal voltage regulator. This is because the core of the microcontroller runs at 2.5 volts. In order to not have any external circuitry, we will enable the internal voltage regulator.
Now we'll talk about the USB mass storage interface. Using a USB Type B jack that is mounted on the Nesi board, we are able to plug the system into the NanoRacks chassis. As we've already indicated, the USB port does provide the primary 5 volts and ground reference to the Nesi board. In addition, there are 2 wires that are used for communications from the NanoRacks chassis computer to the Nesi board. The PIC-24 is programmed to be a USB slave and allows the NanoRacks chassis to access the onboard SD cards of the Nesi board.
This is how the button subsystem sends a trigger into the microcontroller. The digital input pin, pin 64, is held at a high using a pull-up resistor connected to 3.3 volts. When this pin is held high, that means that there is no event occurring. When the button is pressed, as you can see here in the circuitry, the pin is then driven to a 0, which means that an event has occurred. There is an external button access which allows you to add an external button to control the triggered value.
A voltage divider network can be created using an onboard resistor and a resistive sensor, in this case plugged into JP3. The voltage, changing from 0 to 3.3 volts, is passed through a unity gain amplifier into pin 16 in this case, which is configured as an analog input on the PIC-24. In total, there are 4 of these circuits in the system. The value of the resistor is chosen based on the nominal value of the resistive sensor being used.
This slide shows the power output header found on the board at JP10. There are 2 connections for each voltage level, 5 volts, 3.3 volts, and ground.
On board the PIC-24 is a real-time clock module. To provide an accurate clock to the module, we use a 32,768 Hz oscillator. We chose this oscillator because it allows us to easily divide the clock down to a 1-second reference.
The Nesi board provides power drivers to be able to control high-power external devices. There are 2 of these circuits available. Power driver A begins with the ability to attach the 5 volts to an external device, such as a motor, across JP2. Once that is done, the PIC-24 has the ability then to control current flow through that motor using the digital output that's available on pin 3. That output is used as an enable to the load side power driver, which acts as a switch to turn the device on and off. In addition, we have the ability to sense whether that external load is actually receiving power. The resistor network here allows us to create a digital input signal that is routed to pin 4 of the PIC-24. If this signal is ground, that indicates that no device is currently attached or is not working. If the signal is a 1, that indicates the device indeed is drawing current. Similar to the power driver A circuit, we have power driver B. In this case, we use JP16 to determine whether we are going to provide a 6-volt power or a 5-volt power to that external load that is attached to JP11. As with power driver A circuitry, we have another digital output on pin 60 of the PIC-24, which acts as an enable to the low side power driver switch, thus turning on or off the external load.
Here's the CO2 subsystem. We use JP9 to power the CO2 sensor. We would have to connect 2 and 3 together since this is a 6-volt power requirement for the CO2 sensor. There is a heater inside of the sensor that is controlled by the microcontroller. It runs the signal through a low side power driver in order to heat the element inside. The CO2 sensor produces an output voltage relative to the amount of CO2 in the environment, which is the blue line you see here in the graph. It then runs the signal through an offset, which is the red line in the graph. And after that, it goes through a gain, which then allows an analog signal from 0 to 3.3 volts to be produced and sent to the microcontroller.
So here we have our camera, which will be mounted on JP7. It has 2 data pins, transmit and receive, which communicate via UART to the PIC24, and a 3.3 volt power pin. A secondary camera header is available on JP13, so that you have the ability to mount an external camera. By using JP15, you can select one of 2 power options. By jumpering pins 2 and 3 together, the camera will always be on. But by using pin 1, using a low side power driver as a digital switch, the camera can be controlled using the microcontroller.
This diagram shows how the SD memory card slots interface with the PIC microcontroller. Each SD card slot has a chip detect, which serves as a sensor for when an SD card is present, a chip select, which allows the microcontroller to select which SD card to use, and a standard 3-wire SPI bus is used for communication between the SD card and the microcontroller. In practice, only one card will be used at a time.
This slide is the expansion headers on the Nesi board. JP8 is the general purpose expansion header interface. This allows you to connect external modules and peripherals, and also external sensors, for instance. On pin 1 is 3.3 volt power output, and on pin 2 is the ground reference. Pins 3 through 10 are connected to pins on the microcontroller. 8 of these pins are digital I/O, 5 of them are analog inputs, and 3 of them are connected to remappable peripherals. You can configure the function of each of the pins on the expansion header in software.
The Nesi board also has the ability to accommodate external devices through various serial communications protocols. At JP12, we have the ability to provide 3.3 volts and ground reference to the external device should it be necessary. In addition to the power, we have 4 data pins that can be configured through the PIC24 to accommodate a large number of different communications protocols.
Here are 2 examples of using the communications header. One is a UART application where pins 3, 4, 5, and 6 will be used as a transmit, receive, request to send, and clear to send going into the microcontroller, and an SPI application where the master out slave in and the master in slave out, the slave clock, and the chip select will be used.
Okay, here with the LEDs, we'll have a 5 volt power source, which will be run through current limiting resistors based on the maximum current allowed for the LEDs that you use. Here we have through-hole LEDs that are mounted directly to the board. The power for that is going to run through the power drivers, which here are being used as digital switches. When the LED enable is set to 1, the LED will be on. Additionally, you can add surface mount LEDs to the board, and we also have the capability to externally mount LEDs to the Nesi board.
This diagram shows how the Picket programmer is connected to the Nesi board in order to program the device. The arrow on the Picket programmer should be connected to the pin marked with an asterisk on the board. And remember that power must be applied via USB in order to program the device.